All right, so all of this unit, we've been really building up to this final discussion of the physics of climate change. All of our discussion about ways that we produce energy, going from fossil fuels all the way to renewables and nuclear, as well as our discussion about how the sun emits power that the earth absorbs and reflects, has been leading us to this discussion of, okay, all of this is our situation here on earth. What is it resulting in? And then from that result, how should we, if we should, change our behavior to mitigate the disasters or potential harmful effects that are coming our way? So today, our discussion is all about climate change. Now, to get us started, I think it's important for us to take a step back and actually look at some computer models. There have been some models that have been made that can isolate different properties in the model. So for example, isolate the effects of the sun, or isolate the effects of volcanoes, or fossil fuels, or aerosols. And in each of these studies, you can keep all of the other factors constant and only change the one. And then if you're only changing the one in that model, the prediction that you get is as if everything else stayed the same, but it was only fossil fuels that were changing over time, or only the sun. And from that, we can actually select or figure out which of these sources are the primary factor in the outcomes that we see. So we're going to start by graphing the average global temperature anomaly relative to an 1880 to 1910 global average. Now we can see over this last 100 years or so that this global average anomaly has gone up about 1.4 degrees Fahrenheit. That is a pretty significant change that we'll talk about in a little bit. But if we want to figure out what is the cause of this, our best way to do that is to build a mathematical model, because there isn't a great way to do a typical scientific experiment here where we hold controls and see what happens. So instead, what we do is we build a mathematical model that we can do the same thing. Now, in this mathematical model, we can hold all of the other values constant while changing just one variable at a time. So a lot of times, people that are talking about climate change and suggesting that it isn't man-made, uh, point to natural causes that affect the global temperature. So let's look at a couple of natural causes first. First, the Earth's orbit does vary from time to time. The Earth is on a wobble. And as the Earth's orbit changes, we do see some variation in our model, but it is not nearly to the extent of the variation that we see in our observed temperature change. So if we go to the next one, this is often talked about of the sun. The sun, as we've mentioned, is where most of the energy that the Earth has is coming from. That is our primary source of energy here on Earth. But the sun, even though it has some variation, that variation again does not represent this changing temperature that we're seeing. So it does have some factor, but not nearly enough to say that yes, this is where the observed temperature change is coming from. The third one is often talked about as volcanoes. Volcanoes, every time they erupt, these large volcano eruptions produce a ton, many tons of CO2 into the atmosphere. It actually turns out, though, that these volcano eruptions here are seen as negative spikes in the global temperature. The reason for this is, in addition to emitting CO2 into the atmosphere, is also producing plumes of ash that is very reflective. And as the ash is in our atmosphere, it reflects more sunlight from getting down to the surface of our planet. It increases the overall albedo of Earth, therefore decreasing the global temperature. And you can actually see in here, these negative spikes show up in our observed temperature. So it gives us confidence in this model that is hard to see in the noise, but there are some clear negative spikes that are showing up. So if we take these three natural sources and we combine them together, we just average these three natural sources of change, we see that overall this does not present a strong argument for this temperature change that we are observing coming from natural sources. So let's look at some more man-made factors. The first of which is deforestation. As we change some naturally forested areas to more urban, or even just removing the trees to produce just a barren landscape, it actually has a decreasing effect on the global temperature. And the reason for that is, again, the albedo effect. So as you are losing these forests, the actual reflectivity increases, which decreases the temperature. Ozone is also pointed to. Ozone heats up Earth's surface as well, so it kind of works in a similar way to greenhouse gases, but it is not nearly enough to account for our observed change. Aerosols, interestingly enough, have a negative factor as well. So actually, some people have proposed one way to combat climate change is to release more aerosols into the air. Um, the harmful side effect of that is aerosol is primarily the ingredient for acid rain. So there are many negative side effects of that, but aerosols on their own would have a decreasing effect on the observed global temperature. And then, of course, let's look at greenhouse gases. If we plot that out, we can see that greenhouse gases of these different factors that we've looked at has by far the largest impact. It's actually even higher than the observed if we control just for the greenhouse gases and keep everything else constant, because some of those actually had a negative effect. So let's go ahead and average all of those man-made factors together. So plot them all together and then we'll average them up. And we can see that they average very, very closely to what our observed climate is looking like. And then let's go ahead and factor in those natural sources as well. And we can see how good our model is at predicting what we're seeing. And this model, you can see, is a really good predictor. Everything from these little spikes from some of those volcano eruptions to this general increase to get us to about that 1.4 degrees Fahrenheit anomaly. This model matches up really, really close. So with that in mind, let's go back and talk a little bit more about this CO2 and um, greenhouse gases and how they factor in to our conversation about climate change. So given these different models, we can see that the temperature has been rising. Now this graph here is showing the actual measurements that are globally averaged and their anomaly from some reference temperature. Now you can see that the reference temperature where 0 is probably set somewhere as like an average in the early 80s or early 1800s rather. So as you can see, those models are great for helping us to pinpoint what the primary source is that is leading to the outcome. Now, this graph here is showing us the actual measurements that have been made over time of the average global temperature. Now, this here isn't actually showing an average global temperature, but it's showing the differential between some standardized average. So the way we describe this is actually called a temperature anomaly. Now, a temperature anomaly is just how far away from you are from this set point average. Now, where this temperature anomaly was set for this NASA graph was somewhere in the early 1800s. So you can see it actually, the temperature had a lower average temperature for many years before now we've started to see that temperature anomaly start to rise. And you can also see in this graph there's kind of this jagged line behind this smoother black line. There is a difference between climate and weather. Now, from year to year, you might see some fluctuations where like one year might be on average a little bit colder, but the next year is on average a little bit warmer. And those fluctuations smooth out if you take an average over like a 5-year span. And the same thing happens from month to month or day to day within the year. Just because you have cold days doesn't mean the overall temperature of the Earth isn't rising. You have to look at that overall trend to really be seeing what the climate is doing. Now, as you saw in the models, the primary factor here was carbon dioxide concentration. That was by far the best predictor of this temperature change that we've seen over the last 100 years. Now, there was a scientist at the Mauna Loa Observatory. His name is Keeling, and he was the first one to start taking daily, actually multiple times a day, measurements of the carbon dioxide concentration. And this record goes back now about 60 years. And we can see that over the last 2 years, there are some rises and falls in that. If we zoom out a little bit, because we have the data to do so, before we do, just to keep as a reference point, 415 parts per million, that is the latest CO2 reading. And this measurement was taken very recently on April 24th, 2020. So 415 parts per million. That's your reference point now. If we zoom back a little bit, you can see those 2 years that we were just looking at, that's right here on our graph. And now we're zooming back 60 years. This is the entire record of that Keeling data. So this carbon dioxide concentration taken at the Mauna Loa Observatory. And you can see that rise and fall. We'll talk about that in a little bit. This kind of stair-step razor blade sort of pattern, jagged edge. And you can see that over this 60 years, the parts per million have risen from 320 or 315 all the way up to that 415. We have increased about 100 parts per million. That is a significant amount. If we zoom back even further, and we can do this by using some ice core data, we can go back even farther, all the way here for 300 years. And we can see that before that, the concentration was even lower. It goes down to about 275 parts per million. And sometimes we call this, this is known as like the hockey stick graph, where it's pretty flat for a long time. And then in recent history here, we see this sudden spike in CO2 levels that is growing at an exponential rate. If we zoom back even farther, we can see that there actually has been some fluctuation in CO2 levels over the years, but not within the last 10,000 years. This is even more of a hockey stick graph. It's flat for pretty much 100 or 10,000 years before, in recent history, this last 50 years or so, we've seen this sudden spike in CO2. If we zoom back even farther, we can start to see those fluctuations that sometimes you'll hear about. That over the last 800,000 years, again, this is taken with ice core data, we can see that there are natural rises and falls in this CO2 concentration, but nothing in the order that we've seen in the last 50 years. Again, we are now currently at about 450 or 415 parts per million. So that means there are 415 molecules of CO2 for every 1 million molecules there are in the atmosphere. This number never really rose above 300 in this measurable history of Earth. So 800,000 years, we are about 100 parts per million higher than we have ever been. Now, this is really, really nicely seen in an animation. So I want to show you this. It's the same data that we just saw, but you can see it zooming out in real time. All right, something that I've referenced but haven't really talked in detail about is this weird stair-step jaggedy line that we're seeing in this graph. Every year of this data, we see this spike that happens in the northern hemisphere's summer. And you could actually count these spikes like rings on a tree to figure out how long this data goes for. Now, this fluctuates because of seasons. There are differences in the CO2 because as plants grow, they soak up some of the CO2 that's in the atmosphere, and as they die in the winter, they release that CO2 back into the atmosphere. Now, a question that I have for you is, the Earth has a southern hemisphere and a northern hemisphere, and at all times in the year, one of those hemispheres is experiencing summer. So why do we get this jaggedy line? Why don't they just cancel each other out? The answer is because in the northern hemisphere, there's actually more land mass than there is in the southern hemisphere. Now, this primary change in the seasons is seen most noticeably over land. So, since the northern hemisphere has more land and then has more plants that live on that land, uh, this jaggedy line follows the northern hemisphere. The southern hemisphere's summer cancels it out a little bit, but not enough to totally smooth out this jaggedy line. So if we're going to talk about CO2, we need to talk about how CO2 is actually affecting us in terms of climate change. Because CO2 is a natural um, byproduct of nature. Carbon dioxide in itself isn't harmful. You are all exhaling carbon dioxide right now. But carbon dioxide in large quantities starts to change with the delicate, but carbon dioxide in large quantities starts to affect the delicate balance of our atmosphere. So if you start to get too much carbon dioxide to throw off that balance, you get a runaway greenhouse effect. Now, some greenhouse effect is good, but too much starts to mess with our energy balance here on Earth and starts to heat up the world. I want to show you a quick clip on how the greenhouse effect works, and then we'll come back and discuss that in a little bit.
The Earth and the Moon are basically the same distance from the Sun, yet temperatures on the Moon average an unlivable -18 degrees Celsius, and even deadlier, they range from -170 Celsius during lunar night to 100 Celsius at lunar noon, regularly exceeding both the coldest and hottest temperatures ever recorded on Earth. And while the days and nights on the Moon are about 14 times longer than those on Earth, our planet's relatively fast rotation isn't what spares us from those loony temperatures. What protects us is our atmosphere. By day, it serves as a shield, blocking out the most harmful and energetic of the sun's rays and about 1/3 of the less intense but visible light. At the same time, it traps the infrared radiation, aka heat, radiating out from Earth's sun-warmed surface, keeping us from freezing solid at night. In order for our atmosphere to absorb any kind of radiation, it needs to have some electrically charged particles for passing electromagnetic waves to push around. And most of our atmosphere is made up of gas molecules that don't have an electric charge. They all have a balanced number of positive protons and negative electrons. But some molecules hold most of their negatively charged electrons closer to one side, lending them a lopsidedness that can jiggle back and forth to absorb the energy of incoming infrared rays. For example, water, ozone, and nitrous oxide are all electrically lopsided, so they all absorb infrared radiation. Then there are gases like carbon dioxide and methane. On paper, neither molecule looks lopsided, so it doesn't seem like they should be able to absorb any radiating heat. But in reality, gas molecules aren't motionless. They crash into each other billions of times per second, knocking each other in different directions and also into different modes of rotation and vibration. And it turns out that both carbon dioxide and methane spend most of their time shaking it in electrically lopsided ways, allowing them to absorb infrared rays and help insulate the Earth. Even though many different kinds of molecules can absorb infrared radiation, the vast majority of our atmosphere can't, because it's made of nitrogen and oxygen, which don't get lopsided even when they are vibrating. They're too symmetric. Nevertheless, the lopsided 1% are such good infrared absorbers that they manage to intercept about 90% of Earth's outgoing heat. Each captured ray gets pinged around the atmosphere, and most end up returning to the surface at least once before escaping to space. We don't need to visit the moon during frigid lunar night to know just how important the game of radiation pinball is for Earth. Ice records from our own coldest climate show that small natural variations in atmospheric carbon dioxide produce relatively big changes in temperature. They also show that, compared to the last 800,000 years, the game today is much, much harder.
As you saw from that video, the way that the greenhouse effect works is actually a little bit different than maybe you've been taught at some point in your lives. Typically, I remember thinking and learning that the greenhouse effect was the carbon dioxide molecules or our atmosphere bouncing this energy back to the Earth. But the reality is not quite like that. It doesn't bounce. Instead, it gets absorbed and re-emitted. So these gas molecules are the perfect resonant frequency that it matches the infrared radiation that's coming off of the Earth as heat. Those molecules absorb that energy, and then as they're jiggling around, they actually re-emit that energy. And some of that, because it's re-emitting in all directions, some of that is going out into space to be lost. but some of that is coming back down to Earth. So it doesn't trap all uh, thermal radiation, but it does trap a percentage as the gas absorbs and re-emits this radiation. So again, this happens because the molecules match the resonant vibration frequency of that infrared light. Now, in the past lesson, we ended by talking about the greenhouse gases, and I really expect you to know these top three. So, number 4 is nitrogen oxides, number 5 is oxygen and ozones. But there are three primary greenhouse gases that lead to this effect that was shown in the video in the last slide. Number 1 is water vapor. You can see from this graph shown in the blue, this is by far the number one. And most people don't realize this. Water vapor, it's there. It's not really something that humans are changing to any noticeable amount compared to some of these other ones. So we don't really talk about it in terms of climate change and humans' effect on the globe. Number 2, though, we talk about quite a bit is carbon dioxide, and that's what we've been referencing. And that's honestly why we talked about fossil fuels and the need to switch to renewable at some point is for this reason of carbon dioxide, that fossil fuels emit carbon dioxide, but things like nuclear and renewables do not. So if we need to limit carbon dioxide that we saw in that Keeling curve, we need to move towards more renewable resources. And then number 3 is methane. We're not going to talk too much in depth about methane in this class, but you probably have seen some examples of that, whether we were talking about methane being released in the permafrost that is melting, or methane being produced in different agricultural facilities. You've probably heard of cow farts releasing a lot of methane. A lot of agricultural processes produce a ton of methane, which is a huge factor in the amount of greenhouse gases that are being emitted by humans on our planet.